Hi, good morning. I'm Uday from Initiative-IQTI. So, we have a distinguished speaker joining us today, Dr. Atulasimha Jayasimha, the Kumanda Professor from the Department of Mechanical and Nuclear Engineering, Electrical and Computing Engineering at Virginia Commonwealth University. Dr. Jayasimha is an expert in nanomagnetism, spintronics, non-volatile memory, hardware AI, and quantum computing with spins. His research has significant implications for the field of computing and technology. Today he will be delivering a talk on the topic of nanoscale magnetic devices, applications to hardware AI, and quantum computing. In his talk, Dr. Jayasimha will address the key challenges in classical and quantum computing and discuss how nanomagnetic devices can provide potential solutions. These devices have shown promise in enabling energy-efficient computer memory and hardware AI for edge or IoT devices. Additionally, Dr. Jayasimha will explore how nanomagnetic devices can be used to control and manipulate spin qubits, allowing for advancements in quantum computing. Now, without further ado, I invite Dr. Atulasimha Jayasimha to begin his talk.
Thank you. Thank you for the introduction, and thank you for the invitation to give this talk. I'm going to talk today about hardware AI and quantum computing, and specifically connect my work on nanoscale magnetic devices. But in many cases like hardware AI, the use of nanoscale magnetic devices are exemplary in the sense that you could take some other device like phase change or resistive memory and work through a similar process. So I'm from Virginia Commonwealth University, affiliated to all these departments. And then I'm going to start by explaining something about computing, energy required for computing, so that we have a big overall picture. And then I'm going to go into fundamental materials work, which could address some of these grand challenges of computing. And we'll start first with something which is a non-volatile memory, closer to commercialization, that kind of idea, not very far. And then see how this kind of a memory unit could be an enabler for classical AI hardware as well as for quantum computing. So of course I should acknowledge all my various PhD students who have worked on different topics, and then the various collaborators and their groups that I work with. The way the talk will be outlined is we will first look into computing itself, then look at some materials and devices for memory, and then go into AI and quantum computing. So maybe at the end of each block, I can stop and you can ask if you have questions so that we can clarify things as we go. So one of the important motivation of why people are looking for energy efficiency in computing is the cost of computing, right? So for example, a single Google search takes 1 kilojoules of energy. So if you do 2 trillion searches a year, that is the cost, right? And if you look at the consumption of energy by a single company in 2019, it exceeds that of some countries, right? And this is growing exponentially. So very soon, our cost in our society is not how much energy you consume or how much carbon dioxide you emit by going in a car or plane from here to there, but just for doing a computing, right? And that was not significant, but it is increasingly becoming significant. And therefore, we have to start addressing the issue of energy efficiency of computing in the long run. There is another important reason why we look at energy efficiency, again, whether it's classical memory or AI. There are lots of devices that are working at the edge, right? And they don't either have the hardware resources or the energy available or both to perform certain massive computing. So what do? All this information is being sent off to a server, so you are wasting energy in communicating, then there's a lot of energy spent in that server, and then you're getting that information back. So that is both energy inefficient and opens you up to attacks. It's not, there are vulnerabilities there, right? So in general, we want to do energy efficiency computing, both low energy and with low resources. That's kind of the overall motivator of the talk. Now let's jump back and look at some fundamental limits of computing. Now there are many people who have looked into these issues of what is the minimum energy with which you can get away with computing. We are nowhere close to that limit, practically speaking, but it's still an interesting theoretical question to ask. And one of the things that comes up is to relate computing with something physical. So you're storing information physically, there is entropy. From those arguments, you can say that for erasing information, this is the minimum energy required. However, we have also looked into this problem in a slightly different way. For practical computing, it's not just the minimum energy, but I need to do computing with very good reliability, right? So if you have an AND gate, so all of you are aware of an AND gate, and it has to execute some truth table, it should do that correctly with a mistake probably 1 in 10 to the power 15 times, right? Anything less is not acceptable. So there is a cost associated with that as well. And a very simple way to look at it is, in physics, you have a barrier, and you have one state here and one state here that degenerate, right? So a good way to look at compute is you lower the barrier. Now you can occupy both states. You tilt this barrier. The more you tilt, the more deterministically you will go to this state, right? So you can think of all other schemes, and there are very clever thoughts about it. You can remove this barrier, then exactly at the barrier is low, you can modulate this barrier, make it up. But this requires a lot of time synchronization, right? So one way of being very sure is to tilt. The more the tilt you do to the barrier, the greater the energy you expend, and that gives you error resilience, right? So that's a fundamental view of computing. In fact, we did a simple calculation. For example, if you have this barrier and you tilt it as much as you want, and you wait for it to equilibrate, you will get a Boltzmann distribution, assuming this is classical. And then when you raise this barrier, these all switch correctly and these don't switch. And from there, you can say, okay, if I spend 1 EV of energy, I can probably get off with an error rate of 10 to the power minus 9 and so on. So why are we looking at nanomagnets? And again, the philosophy keeps changing. So if you look way back in the 80s, when I talked about many of those leading figures came up with what is the necessary energy dissipation to compute, the reason people pitched some correlated systems like nanomagnets are this. Suppose I have a bit with one state 0 pointing up and another pointing down, then the energy required to switch is kT log 1 by p, where p is the error factor. I just said earlier that if you want very deterministic switching, you tilt the barrier a lot, you dissipate a lot of energy, and then you will switch with high precision or low error, right? So now what happened is, if you take a correlated system like a spin, this could have 10 to the power 4 spins, but they're all exchange coupled to each other. They switch coherently. So it's like 1 degree of freedom. But in reality, it really doesn't switch coherently. There is some decoherence, and so you get few kT log 1 by p, right? And with the transistor, this n was large, the number of electrons being pushed into the channel. But as that is becoming smaller and smaller, there's really no significant advantage of these correlated systems like a nanomagnet over a transistor or a CMOS device, right? So then why are we still looking at it? Because there are other potential advantages, and that is where the thinking is now. First, there is what is called non-volatility. So if you have a CMOS or a transistor, you put electrons in the channel and you take away your voltage, what happens? The gating is gone, so you are not able to keep that information. In this magnet, there is a barrier of 40 kT or 1 electron volt between up and this state. So if you don't do anything, this information will stay there for centuries. So you don't have to keep the power on to store information. So this is very important for memory, increasingly becoming important for AI, because what do you do there? You have all these synaptic weights. Once you have learned and you are doing inference, those weights don't change, and you need to do some kind of multiplication of etc. with those weights. And if you could make them multi-state and non-volatile, and you could do this entire multiplication in the hardware, it would be extremely energy efficient. Why? Because if you have to fetch information, multiply it, put it back somewhere else, you're spending so much energy going back and forth, and there's also a bottleneck. That is what you can solve with these non-volatile memory devices. And then we'll go into it. There are other things like physical reservoir computing, which can also do with magnets. So to summarize, if you look at our work with magnets, we look at magnets because it offers its non-volatility and also good nonlinear dynamics. We'll look at it later. There is also an easy readout. That problem has been solved. The on-off ratio, that is parallel to anti-parallel, maximum room temperature is 7:1. Practically you will get 2:1 or 3:1. Good enough for memory, not for logic. And the big challenge is the internal energy dissipation in that magnet is very little, right? So that's the advantage. But if you want to switch this, let's say from this way to this way or from up to down, you need to apply either a field or a spin polarized current. So if you're applying a spin polarized current, what that means is you inject electrons, they get polarized, and in turn they polarize this layer, right? That I square R loss there, even today, even in 11 nanometer diameter MTJ, is of the order of 100 femtojoules. Whereas the power it requires to switch, or energy to switch a CMOS device, is just 100 attojoules. So you're getting this non-volatility or holding information at an enormous cost, and that is definitely too high. So at the fundamental device level, we have over the past decade been looking at various ways to switch with electric fields rather than currents or magnetic field. One is strain, and I will not talk about it today, where you use strain to change the spin orbit coupling and therefore the anisotropy, and that's how you switch magnetization up and down. There's another method which is called voltage control of magnetic anisotropy, where you apply an electric field that changes the density of states in your ferromagnetic material, and that changes the anisotropy from out of plane to in plane. So we will discuss this in conjunction with a thing called skyrmions later. But just to summarize what I have said so far, this becomes very interesting because there are lots of materials, lots of interesting properties, lots of devices you can make in the lab, but ultimately the one that will win in, or has the possibility of winning in an actual hardware chip, must also go well with the circuits, the architecture, and ultimately the algorithm. For example, I can have my non-volatile memory that has 5 states or 7 states, right? But then the traditional synapses are 32-bit. So can I have an algorithm where I can use this very low resolution or few number of states nanoscale device in hardware and still get state-of-the-art recognition when you're talking of AI? So this summarizes the lessons for computing, or what you need to look for specifically in classical hardware AI. So do we have any questions at this stage? Or any clarifications? If not, I will move on. So, okay. So now we step into nanoscale devices, and before I jump into work on actual nanoscale devices, let me just talk of the various energies that define the landscape at the nanoscale, right? So with this background, it's easy to interpret what is happening. So if you have a nanoscale magnet or even a macroscale magnet, piece of iron, there are different interactions. The first is the exchange interaction, where one spin wants to be always parallel to its neighbor. That is the low energy state if it's ferromagnetic. If it is anti-parallel, then the energy cost goes up, right? And then we have what's called demagnetizing energy. So if you have something which is elliptical or needle shaped, your magnetism always wants to point this way, not this way. Why? Because the stray fields here are much smaller than making it point this way, and that also motivates how your magnetization orients. And then of course you have the Zeeman energy, which is orientation of the magnet with an external magnetic field, and then you have other anisotropies, which could be like in the crystal structure you have one preference of direction, or because of the interface and the material you put on it, you could force the magnetic spins to point in a certain direction. So if you put all this together, now you can say if I have a very tiny magnet here, all my spins want to be parallel, they are exchange coupled, and they will point along the long direction, right? It takes energy to actually rotate it to this direction, so this is not favorable. That's why you have an energy barrier between the up and the down states, which I was talking about. That brings non-volatility. What about if you make this bigger? This is probably true for 100 nanometers. If I go to a micron, then those spins can all rotate like this ever so slightly, right, and form a vortex, but they are not strictly parallel, but they have enough atomic lattices to perform this rotation that are almost parallel to each other, but they can perform this rotation, right, and therefore a nice ring or vortex state may be the most stable. And it goes on, but this gives you all the terms. Now we are going to look at one other term which is extremely interesting, and I told you exchange wants your spins to be all parallel to each other, correct? But there is another term called a Dioshensky-Moria interaction that occurs because of a 3-atom interaction. So there's an atom here, there's a heavy metal atom, for example here, sometimes topological insulator, and then there is another atom here. These two mediated through this other atom want to be perpendicular to each other, right? So you have one asking you to be parallel, other asking you to be perpendicular. So what the emergent property of that entire ensemble or the collection of spins is each spin will rotate like this and form a skyrmion, and this such a skyrmion is also called a protected state because you see the core is pointing down and then this rotates all the way and the periphery points up. You can have rotation like this would be nil, or you could also rotate like that, that will give you a block skyrmion, but these are the technical details, but you can get very interesting structures like this. So now let us ask ourselves the question, why are we, so to summarize, we have this strain that I don't talk about, we have this voltage control. Using this strain and this voltage control, which are two additional handles, and these various energies, how can we use it for some computing device? So let me start with an experiment which is not on a computing device, it is on a film, and what we are trying to do is that skyrmion state that I just described to you earlier, we are asking ourselves, can we control that purely with a voltage, right? No, that is only electric fields allowed, no magnetic fields, right? And so in summary, what you have here is a very complex structure, tantalum, iridium, manganese, Co-Phoebe. The reason you have iridium, manganese, Co-Phoebe is because there is exchange bias coming from antiferromagnet layer to a ferromagnet layer, which then means that you don't have to apply fields. And then there is also the Co-Phoebe MgO interface where the oxygen P shell and the D shell of these interact in such a way that when you apply a field across this, you can change the anisotropy from in plane to out of plane. And in steady state, we get this nice skyrmion state. The way you prove it's a skyrmion is you go with a magnetic tip that is oscillating. If you have looked at an AFM, it taps, 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 tells you the topology, it lifts up and then taps again, and then the magnetic field, whether it's like this or like this, will make a difference to your tip depending on the way you magnetize the tip. From there, you can actually map and say, if I go near a skyrmion, this is the stray field at 40 nanometer height from the skyrmion as I go across, right? And we can prove that we get that very exotic state at room temperature in a stable way where you can do multiple scans. There's another way you can prove that you have a device like a skyrmion. You put a current, and then instead of going in a straight line, it curves. So have you ever seen a tennis ball or a cricket ball, what happens when it spins? In addition to the drag and other forces here, there is also a force in this direction coming from the spinning called the Magnus effect. So whenever you have a magnetic structure that has a net curl like a skyrmion and you try to move it, it will curve, right? So looking at the curve and looking at this, you can actually prove that it is a skyrmion. But more importantly, what we can prove is we switch on the field, we destroy the skyrmion, right? We put a field in the opposite directory, we recreate the skyrmion. In other words, no magnetic field applied, pure electric field, we are able to destroy, create for many cycles, and this is like initial, annihilated state, final state. So what is happening here, if you want to know more, if you go back to the slides, when I don't put any field, I have this large anisotropy, right? But then if the anisotropy is lowered, what happens is that there is this thing that says don't be parallel, go perpendicular, right? So you form this skyrmion state. But if I say no, I want all spins to point up or down, how do I do it? I apply a voltage, make it anisotropic, force it to be in this state, I will completely annihilate and get a ferromagnet. The next thing I will do is I will then reduce that anisotropy by applying opposite voltage, and then this wants to form a skyrmion. So that's exactly what we see here, right? So this is a good experiment where we prove that we can do voltage control, but we are nowhere close to a device. So let's see what is the connector now. Why are we interested in doing a device? So to do that, I told you the basic problem with our existing commercial magnetic memory is this. You can buy a 1 GB STT RAM off the shelf from a company, right? But the energy required to switch this is enormous. So it's not used for all applications, it's used only for specialized things. So the aim is to reduce that energy by not switching with currents and fields, magnetic fields, but by electrical control. So in a research setting, people have used voltage control to switch from here to here in about an array of 1000 bits, right? That has been demonstrated. But what's the problem there? You go here, you apply a field, you go to this direction. But then if you let go, you can either go this way or this way, right? So to bring determinism, people put a bias field and make this precess around that bias field. So if you exactly remove your voltage pulse, it will go down, right? So we have already gone, at least in a proof of concept demonstration, not we, another group, has shown that with, this is not the skyrmion, with just voltage, you can switch from up to down, but there is an error in the switching process because of this stochasticity involved. But we have shown with simulations that instead of just going like this and precessing and coming down, this is what has been demonstrated. If we can go to an intermediate skyrmion state, what happens, all your spins are up, you put a voltage, you are able to keep your center spin like this, your peripheral spins like this. When you raise your anisotropy again, because there is more surface area here, this will move in and squish your spins and make it switch down. And because you don't have this kind of precessional dynamics, even if you introduce noise like thermal noise, disorders into the process, you see your switching error does not change. There is always a window where you can switch to very, very high accuracy. Whereas here, if you inject all kinds of thermal noise and disorder, you don't get the switching, you start getting 2%, 3% error, which will then kill your memory. So this is why this very basic research could be a potential solution to then do something which is more of a technology, right? And without going into too much details, we have looked at if we can scale to 20 nanometers to make it state of the art. And here is an example where the skyrmion that we did on film, we are trying to look at what happens in a 100 nanometer dot, right? So this is then closer to actual technology compared to the physics that I had talked about earlier, and so this is the process. So I will stop here with the skyrmion manipulation and memory devices. Any questions at this stage? Oh, no, we didn't choose to place the atoms there. So if you have a film, right, what happens is because of the balance between all these forces, the DMI, the exchange, etc., you have skyrmions at certain places which you cannot control. But in a memory technology, I don't want skyrmions on a film, right? I want it in a particular disk. That disk is one memory element, right? So it is deliberately placed there and it has to be created. And ultimately, I don't want a skyrmion itself in the steady state. I want up, skyrmion down, so that you can do the switching process. So that's the idea there, right? So now we talked about memory. Let's look at how these devices would be useful for something like neuromorphic computing. So again, as a very brief idea of what happens in some implementations of most implementations of deep neural networks, you have inputs coming out from different neurons that fire, then you have weights, you multiply this by the weight, and then there's also a bias, you sum all this, and that is input to the next neuron, right? So the idea here is people have looked at various ways of even looking at other exotic ways of making these neurons, but before just to stay focused, we will only look at the synapses, right? And these synapses, can we make them non-volatile? If you make them non-volatile, then once you have that resistance state, it's there forever. So I can put one resistance here, one here, one here, one here, and then that keeps me going, right? So the question is, after I remove power, it should have the same state. And what we are investigating is these nanoscale racetracks, where you can put current for some length of time and it will go here or here or here or here or here, and then you think of the magnetoresistance of this. So if this was a big magnetic tunnel junction, then if you are here and everything is parallel, it's a low resistance. As this progresses, the resistance would be higher and higher. You could get, for example, 5 resistance states. The next question you will ask me is, if typically I'm using a 32-bit floating point, high precision weight here, what is the use of just having 5 states? So that's when it becomes a connected problem. So we solved some very interesting device physics here, where if you push this with some kind of a spin torque, or it's called a spin orbit torque, because you pass current below the layer and then that brings spin polarization, which is moving your magnetic domain, trying to make something that's all like this to go all down, right? So that is what's the domain wall there. So here, let's say the white, everything points up, black points down, and then there's a rotation like this at this region, and you're going to move this so that you change the resistance state. So when you apply certain things, in this case, for example, we applied the same current, but you change the voltage and therefore change the anisotropy. You can control where it goes, but you can never control precisely where it lands, right? So in other words, if I intend to go to state 3, yes, 70% of the time I will go here, but maybe 10% of the time I'm stuck here, 10% of the time I'm stuck there. So now we are starting with a device which is very crappy, right? Only 5 states, highly stochastic, it should not work. But very interestingly, it turns out that if you do things correctly in a deep neural network, it works very well. The reason is, the trick that you should do is when you're training these weights, you don't use 5 bits because they will blow up. You can't take derivatives with very coarse things, right? So you train it with very precise bits, but then when you actually write these bits, you clip it and round it off and put it there. And more importantly, you know that these weights keep changing, so you don't change it all the time, only when it crosses a threshold you change it. And the other interesting thing is, when I write a bit, after I calculate with the algorithm what the weight should be, I'm never sure I will get that weight. I will get some stochastic distribution around that weight. But if I had to do it in software, I had to get random numbers generated, add them. That comes at an enormous cost. Now, starting in hardware, I have my good Boltzmann statistics, I have a crappy device, and I'm getting all that noise for free, no cost, right? And the interesting thing that we show, at least for very simple algorithms, this is MNIST image recognition, is with the right tolerances, you see what happens. My 5-state quantization, which is only 5 states, same network topology, noise added into the system, starts functioning almost as good as a 32-bit floating point, right? So there are cases where your hardware AI is not only efficient, it could be almost close to state-of-the-art efficiency if you are able to do things rightly. Now, I should also say that this is for a very toy example. When you're looking at MNIST, there are much, much bigger problems like CFAR images that also it appears to work. We are in process of working transformers where you need to know whether this is scalable. But this is interesting. The other more physicsy idea, or because it's really rooted in the physics, it is what is called reservoir computing, right? So an example or how to explain this is when you're trying to have a sequence of events, right? And I want to correlate what I said now to what I said maybe a minute back or whatever period of time, I need a signal to kind of interfere with itself, right? So if you had a traditional neural network, what you do is you have to have it recursive in the sense that there's either connection to the own state with a delay or a connection to the connection to a backward state. It cannot be one way. And that introduces a lot of problem in training, right? But if I do it in hardware, what I'm doing is I'm having all these magnets put in here. I give a signal to this magnet, this couples with this. So I'm looking at this spin state and I kind of start a spin oscillation. Because of dipole, it makes this oscillate, this oscillate, this oscillate. It has its own loops, right? Because this will then do, as long as the damping is low, it will do all this and then come back to itself. So when I put information at t equal to 10, I had information at t equal to 0 that is coming back and interfering with that. And that could effectively do a compute. But what is the problem that you have here? You can't change these weights once you fabricate your nanomagnets. All you can do is take your last layer of outputs and do a linear regression there, right? So you have this very powerful nonlinear recursive network, but you cannot, it's an advantage because you don't have to train these weights. It's a nuisance to do it as the length increases. So you don't know how complex of a problem you can solve. But that's all the disadvantages or the inflexibilities, but the flexibility is all you're doing is calculating what weight should I add to each of this output to come up with an answer, right? So we are looking at various cases. We would start with square and sine wave recognition. There are some things called short-term memory, and we see how this increases and so on. But interesting results are two things. One is such computing. You can actually fabricate these magnets. Of course, we now don't make electrical contacts to them, but there is dynamics, and you can visualize this dynamics optically or some other methods in some time domain as well, and then try to use that to actually show you can do computing, which is the process we are working on. But theoretically, at least, you can simulate a whole bunch of magnets like you did here and show that this is what's called a Mecki-Glass time series prediction. It's a stochastic series, and you can train your network to actually mimic this, right? And you see for short time periods, you have almost precise predictions. As you try to go more advanced in time, you may get some small errors. So this is another interesting area where you can have hardware AI at the edge, because your resources are small, but the question is how scalable is it, or what level of complexity are the problems which you can handle. So now I'll stop here before, yeah. Right. 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 Exactly.
As per your designing a hardware for an AI,
right?
For hardware for an AI, you are just using that nanomagnets for a weight.
Correct.
So
yes, exactly.
After after we don't provide a electricity or provide a energy to store
sure.
constantly that, still it will work that model.
Yes.
But do you think it is an efficient way? Because
okay.
For now, mostly if you try to implement any machine learning model or neural networking model, they try to prefer which are been pluggable or means modifiable or editable.
Sure. So this is a good question. So I have to qualify what I mean by that is non-volatile. So it is not that you're not capable of changing the state. So first is it's binary, it's up or down, that was memory, we moved away from it. We are now in multi-bit state. So you have, let's say, 5 states. You use a current to write state 3 or a voltage or some way of writing that state, and then you can do inference. But then let's say you do one cycle of inference and you have to train that weight. So then you can go back and change it somewhere else, right? But once you iterate and solve on one problem, you can use many inferences. But if your problem changes, you can retrain the weight. So it's not that it is hard encoded, you can change the weight. The only advantage is once I've written the weight, I don't need to keep the power on. So that is the advantage, right? So
and one more question, I didn't get you properly when you said that when the output we get, when you were saying that I didn't get it, and then after we have to do again linear.
Okay, so I'll clarify that a little by putting in this structure here. So what I'm saying is, the first approach, we are taking each of these weights, and for each of these connections we are putting a non-volatile element. The nanoscale magnet was exemplary. You can have various other devices which have this non-volatile resistant state. Then when I went to the reservoir computing, what I said is there are absolutely no connections here, no connections here, no connections here, correct? Why? Because I have a magnet here, I have a magnet here, but when I change this magnet, this changes because of dipolar interaction. If I put them on a template where there are spin waves, I can even have spin wave interactions. So all these connections are coming from physics. I have no control over them, right? And then the other thing is, just like this can change this, this can change this if you have dipole. If you don't have reciprocity, then you can make it go one way, etc. So you can do all those things. But once you have made your fabric or your nanomagnets, you cannot change any of these, right? So what do you do then? This system offers you some recursive and some nonlinear behavior, and then you have all these output nodes. So then you say this output has multiplied by this weight, this by this weight. These weights, I will train it with linear regression. So it's almost like if this can work for this problem, this problem, this problem, I can learn to any problem, right? But then because I can't change this, I can't go too complex.
Means because of that noise, we are just using to reduce the error using linear regression.
No, it's not error here. So you see, there is no opportunity to train this network. I'm giving an input, I want an output. So when I give an input, I'll predict some output, but based on it being desirable or not, I need to go back and change the weights. All I'm saying is I can't change this weight, or this weight, but I can change these weights because that's how it's designed to be. Consequence is I don't have all the power I could if I could change these weights as well, but then what is the trade-off? How much can you push this problem to solve as complex as possible on the edge with this kind of a device, right? So, okay. So how are we on time? Okay. So the last section would look at manipulation of qubits, and so there are two things here. One is our nanomagnets, and these are not quantum entities. They are very classical entities. I'll tell you why we are interested in using them later. But imagine you have spins. You could have spins in quantum dots, you could have spins in silicon, or you could have, like the way we envision rare earth spins, which are shallowly implanted on a substrate, right? Which have, why would you use rare earth? Because the spins are F spins, so they are more isolated from the environment, so you get higher coherence time at reasonable temperatures. You don't have to go to millikelvin, etc. Right? The question is, how do you control these spins, right? So spins are isolated, they give you good coherence time, but is there a scalable way in which you can control them? So what is the typical idea here? You always have a DC field, which is in this direction. If you look at classical NMR, for example, and then you have a rotating field, right? So you come in with a microwave or an RF, and then you try to make that microwave not a single frequency but multiple frequencies, so that if you have many bits, each one will address one of these bits, right? So that's the typical way people look at many of these technologies, where they look at off chip or at the edge RF coming in and then working on your qubits. Our idea is we have these nanoscale magnets which we know how to control with voltages. And interestingly, the semiconductor technology is already there to make what are called crossbars. How does a crossbar work? If I put plus volt here and a minus voltage here, then there is a selector diode which gets triggered at the junction between these two, and only this device is actuated, right? So by using the crossbar, I can arbitrarily access any nanomagnet I wish to do, right? Using technology that's already around. The question is, if I can then make this nanoscale magnet work on a proximal qubit, right? So what I'm doing with this magnet is going up, down, right? And that's generating a local RF, and we'll calculate how much that local AC field is just using dipole because it's near field, and it will go off as R cube when you go to the next bit and next bit. So you're actually trying to do control of single bit by that nanomagnet with proximal control. So the technology or the idea we are developing is to do this. And what our simulations show is, often you can just have a single spin, but the readout of a single Bohr magneton is problematic. So what you would like to do is at least have 25 spins there, right? So then, even then you will have to make many repeated measurements, but then in one measurement you can get much more out of it. The only caveat is the more spins that you have, you will see that the RF field that is generated by this going up and down is not going to be the same on this spin versus this spin versus this spin. So every one of them will rotate ever so slightly more, and that will produce dephasing. So you're going to get faster dephasing because of the spatial extent of spins. So you could do things like you could put two magnets symmetrically, so that if there's one gradient like this, one gradient like this, you try to minimize the gradient, and then you have better control there. And then of course there's another problem with such control. So if you take your nanomagnet and put a nice sinusoidal curve here, right, very clear single spike in your Fourier domain, but the magnet here is not going to respond the same way. Why? Because I have anisotropy, I put a voltage, I beat the anisotropy, beat that, then suddenly switch. So that response is nonlinear. Consequently, you will have all these harmonics in your field produced at your nanodot, whether that is a rare earth or a quantum dot or whatever you have. So the trick is, how do you shape these pulses so that you can get good fidelities? And the way you define a fidelity for this is, if you want to do a pi by 2 or a pi rotation, you're going from here to here, two things can happen. You can overshoot, undershoot. So that is one source of error. And also remember, you're now looking at 25 spins, right? So you can have one spin here, that's dephasing, right? If you look at the density matrix for those spins, then there's dephasing coming due to that. So can you come up with the right pulse? And then we had a collaborator at UCLA, the Louis Bouchard group, that tried from their NMR experience various pulse shaping to, and we could show, in theory at least, we can get 99.9 or higher fidelities, which is state of the art for a single qubit. And then other thoughts are, I talked to you about a magnetic skyrmion. So why would we use a skyrmion instead of a magnet, right? So the issue with the magnet is you get very good confinement, because as you move away, it's 1 by r cubed dipole, right? But ideally, if I could have a spin, a monopole here, then I could get much more confinement in this direction. But there is no spin monopole, right? But if I have a spin emergent state where all the spins are pointing along the cube, then that's almost close to that approximation. But I can't do it in 3D, but a skyrmion may be closer to that, right? So what if I have two skyrmions of opposite polarity, etc., and then try to produce my field here by moving these skyrmions, right? So I may get much better confinement in this distance, and therefore it would be the same way of manipulating as the nanomagnet that I showed, but your disturb on a qubit that is here is much smaller, because you will get local confinement of these fields. So there are other advantages. For example, we know that you can drive these to tens of gigahertz and so on. So, so that's what we are working on. And that brings us to the end of this part, which is looking at how you could work on quantum computing with spins, but then the driving here is a classical nanomagnet. So again, to summarize, energy efficiency in computing, as I said earlier, is the need of the hour, because we spend so much of our energy on actually doing compute. But the solutions have to bridge materials that I showed you on films, their behavior, going from there to actual devices made with e-beam lithography, at least in a lab setting, and then to even look at how they would work with circuits and algorithms to see if they have potential of translation. And then we are looking at voltage control of magnets, are very efficient, there's rich physics, so we looked at memory, we looked at some hardware AI, and we looked at quantum control of spin qubits. So with this, I'm ready for acknowledge my grants and any questions. Yeah.
Thank you, Dr. Jayasimha, for your expertise and insights. Yeah. Also, thank you for your contribution to the field.
Sure.
So if anybody have any questions, you can ask.
Go ahead.
So thank you, Professor, for this talk. It was a very nice talk. So my question is, like, I'm from mechanical background.
Sure.
So we solve high fidelity simulations, models for the computational fluid dynamics. Right. Simulate the turbulent flows and all. So such kind of simulations, is there any application to this, like how we can simulate those high fidelity models? Like we use supercomputers now. Right. So I'm just relating how we can, use this kind of.
To be specific, I don't work as much now on quantum algorithms, so I don't know the answer for speed up for fluid mechanics problems, for example. Okay. But if you're asking if you're interested in doing spin simulations, then if you learn the physics, then the tool sets are not very significantly different from what you have done in fluids.
Okay.
For example, if you have a magnet and you're looking at how this magnet moves, that's solving just a differential equation.
Yes.
Non-linear differential equation, you can use Runge-Kutta and do it.
Correct.
Now, if I have a nanoscale magnet here, right, there are two ways of doing it. If I want to keep track of every spin, then I need to look, it's a not continuum picture. But when you have a big enough magnet like 10 nanometers, 100 nanometers, you really don't put SI dot SJ as exchange coupling. What you do is you penalize their doing this with a del square M term.
Okay.
Right? And at that point, it becomes an FEM simulation. So you can use your knowledge of finite difference or finite element to look at these systems.
Okay.
And just like in CFD, you have packages here also. There are people who have done the work, and then you can write scripts to be able to do those simulations.
Okay. Got it. Understood. Thank you.
Sir, I don't have any question, but as you explained whatever the studies you did about that,
Right.
I think so I had read one research paper related to from UNSW.
Right.
In past, they released one paper related to that they created one quantum transistor. I think so that was related to nanomagnet only, that nano memory only, nanomagnet memory. I think so.
Sure.
I'm not sure you are aware of that or not, but as you said that we can store that state once we once we give the direction of that nanomagnet, we can store that data as a state.
Right. But at the point where you're doing storing a state, as I talk, that's a classical magnet.
Yeah,
because the moment you have 10 to the power 4 spins there is no superposition. It's either up or down. It's classical.
But but in that they were saying that they built a quantum transistor which can store more than that state, just not up or down.
Okay. I'm not aware of the work, but it is conceivable. For example, they can have a single spin, and the single spin could be up, down, or 1 by root 2 up, 0 plus 1 state. And then they will probably have another polarized electron to measure, and then they will do repeated measurements, and from their statistics
They were
find
using,
out.
I think so, electromagnetic separately magnetizing to change the direction of that state. So
Yeah, so it is conceivable, but I have not read that particular.
Hello. Yeah. Thanks, Dr. Atulasimha. Thanks for a very insightful presentation. My name is Ganesh Pai. I'm from Mercedes-Benz R&D, India.
Yeah.
So at the start of the presentation, you mentioned that we're not very far from industrialization on the nanomagnets technology. So can you just a bit elaborate on that as to where do we stand on that?
Sure. So when I say we are not far, it's on a relative scale of things. The quantum is completely very, very far away. The hardware AI, the problem is this. If you say I will use a domain wall today, right? The question is those devices are not made in the foundry, so you cannot tape it out, right? And even if you use nanoscale magnets and then let's say that you can make some magnetic memory with CMOS, it's a huge thing to tape out an entire AI chip, but at least it's close to that, right? We may not be able to do it domain walls, but if you use conventional magnetic tunnel junction, you can actually say I have maybe one day, not very far away, have a hardware chip, right? So that's why that is kind of closer in that sense. Now, if you're looking at memory, what I meant is the STT memory is used in very restricted applications, right? For example, inside they have used it inside an engine of a bike because it's a very difficult environment for you to use CMOS memory, so you can use these things. But it is not widespread because of all the issues that I pointed out, right? So this is a technology that is already there. It is commercial, it's available, but it suffers from these problems. And if your solution to that, I'm talking about this fermion demonstrated on the film, is very much at the level of physics, we understand what's going on. But at least if you have a stack and you're going to only change, and the COFI-B is the same COFI-B that you can create a fermion, that's the same thing used in a magnetic tunnel junction. But if you can engineer the heavy metal layer, which you anyway need for a contact, but this is a different contact from what is used, with some interface, and this works. You can switch from up to down with better error rates. Then you already have all the structure to try it out, right? So in the scales of work, I was just trying to say what the effort is and how some things, if you're piggy banking on what is already there, then you have a better potential, not that it will happen. Even then, there is so many other factors to be worked.
Thank you.
Yeah.
Anyone have questions? Okay, that's fine. We have a small appreciation from QRP, sir.
Yeah. Thank you, and thank you very much.